this is Anand and thanks for coming back to my channel. In this video, we will answer 3 questions. First, what is dimension? Second, how to find the dimension of various derived physical quantities? And number 3, what are the various applications of dimension? Clear? This lecture, I will start this lecture by answering the second question, that is how to find the dimension of various derived physical quantities, and in the due course, ultimately we would end up in answering the first question also. Okay, that is what are dimensions. Of course, finally, we will talk about the applications of dimensions. Basically, there are 3 applications of dimensions, which is in your syllabus. Okay, to find the dimension of any derived physical quantity, remember that to find the dimension of any derived physical quantity, you need to have either its formula, any formula containing that physical quantity, or its unit. So we can reach the dimensional formula, we can get the dimensional formula of any derived physical quantity by starting either from its formula or its unit. Clear? To find the dimensional formula of any derived physical quantity, you must memorize these 7 dimensions. Okay, these are the 7 dimensions allotted to the 7 fundamental physical quantities, which we also call the basic physical quantities. A dimension L has been assigned to length, M has been assigned to mass, T has been assigned to time, theta or K has been assigned to temperature. It depends. Sometimes we take the dimension of temperature as theta and sometimes we take it as K. It would be given in your question. Okay. A has been assigned to electric current. A dimension CD has been assigned to luminous intensity. CD stands for candela. A dimension mole stands for amount of substance. Okay. So let's start finding the dimension of physical quantities one by one. Okay. I will take the example of at least 20 to 25 physical quantities. Starting with velocity, or let's say speed. Starting with speed. Remember, to find the dimension, you can proceed either with the formula of that physical quantity or its unit. Clear? Speed. We know the unit of speed, right? It's meter per second. I'm talking in SI system of units. It's meter per second. Okay. Meter is a length, and length, the dimension of length is L. So we would write it as L upon second is a time, and the dimension of time is T. So we would write it as this. So the dimensional formula of speed would be Lt raised to the power minus 1. Normally, we write the dimensional formula of any derived physical quantities in terms of m, L and T. Since m is absent in this formula, so we can write m raised to the power 0 in the formula, Lt raised to the power minus 1. So this is a better way of writing the dimensional formula of any derived physical quantity. Okay. We write the dimensional formula in terms of m, L and T normally. The second one, let's take the example of velocity. The velocity has the same unit, meter per second, right? Meter per second. But this time, this length is the displacement. In the case of speed, it was distance, right? But since both are length, so since the unit is same, so the dimension must be same. Okay. If the unit of any 2 physical quantity is same, their dimension must be same. Always. So the dimension will again come out to be this. M raised to the power 0, L T raised to the power minus 1. This is the dimensional formula actually. If I ask you what is the dimension of velocity, we would say 0 in mass, 1 in length and minus 1 in time. That is, we will only mention the powers of the fundamental physical quantities. Okay. Length has been raised to a power of 1. Time has been raised to a power of minus 1 and mass has been raised to a power of 0. Okay. So the dimension of velocity is 0 in mass, 1 in length and minus 1 in time. Let's talk about some other derived physical quantity. Let's talk about acceleration. Acceleration, the unit is meter per second square. Meter per second square. Meter is a length, so the dimension will be this, and second square is time ka square. Time has dimension t, so t square. Dimension is Lt raised to the power minus 2. It's better to mention m also in the dimensional formula. So we would write it as m raised to the power 0, Lt raised to the power minus 2. This is the dimensional formula of acceleration. We will say that the dimension of acceleration in mass is 0, 1 in length and minus 2 in time. Okay. Let's talk about force. We know force is equals to mass times the acceleration. That is Newton's second law. It was in your class 9th syllabus. Okay. So See, till now we started with the unit. Now we are starting with the formula. It's up to you. Okay. Whatever you find easier, you can start with it. F is equals to mass times acceleration. So mass times acceleration, meter per second square. This is the unit of acceleration. So we can write the acceleration. Check it. Mass times acceleration. So the dimensions of mass is m. The dimension of mass is m, and acceleration is meter per second square. That means length t raised to the power minus 2 meter per second square. So the acceleration of force this time will be m l t raised to the power minus 2. This is a very important expression. Okay, you are supposed to memorize it. The dimension of F is ml t raised to the power minus 2. See, in closing with square bracket, it only means that we are dealing with dimensions. Okay, that's it. The dimension of force is ml t raised to the power minus 2. This is the dimensional formula, and that we will say that the dimension of force is 1 in mass, 1 in length, and minus 2 in time. Dimensions are the paths to which the fundamental physical quantities are raised to express a derived physical quantity. Okay, this is the dimensional formula, ml t raised to the power minus 2, and the dimensions of F is 1 in mass, 1 in length, and minus 2 in time. Let's talk about some more physical quantities. Momentum, mass times velocity, that is momentum. So momentum is mass multiplied by velocity. Mass has dimension of this, and velocity has velocity means meter per second. That means meter in the numerator, second in the denominator. That means length upon time, meter per second. So the dimension of momentum comes out to be ml t raised to the power minus 1. Right? This is the dimensional formula of momentum, and we will say the dimension of momentum is 1 in mass, 1 in length, and minus 1 in time. Sixth, let's take work. Okay, work. The formula of work is force into displacement into cosine of the angle between force and displacement. See, you will learn about this formula later in your subsequent chapter. And why just this formula? In this chapter, you will come across many new terms. Okay, so have patience. Time will come and you will study about them. For the time being, the only thing I expect from you is to remember the formulas. That's it. Okay. Now, force, the dimension of force is ml t raised to the power minus 2. We just derived it. Okay, ml t raised to the power minus 2. The dimension of force into displacement is a length. That means the dimension will be L. Cos theta is a number, right? And pure numbers has no dimension. Cos theta is a number. Cos 30 degree, right? Root 3 by 2. Cos 60 degree, 1 by 2. Cos theta is a number, and numbers has no dimension. Clear? So just ignore the cos theta part. The dimension of work came out to be ml square t raised to the power minus 2. This is the dimensional formula, of course. The dimension of work is 1 in mass, 2 in length, and minus 2 in time. Okay, let's talk about power. Power is what? Rate of doing work. That means rate of doing work is this, right? Work upon time. Work is ml square t raised to the power minus 2 upon time, that is t. Always enclose these terms with a square bracket, okay? Because that implies that you are dealing with dimensions. ml square t raised to the power minus 3. So this is the dimensional formula of power, and we will say the dimension of power is 1 in mass, 2 in length, and minus 3 in time. Clear? Let's see some more terms. Sixth, seventh, eighth, ninth. Let's take energy. Just take any energy, okay? It may be kinetic energy, it may be potential energy. Energy in all forms, as long as we are talking about energy, it would have the same dimension, okay? So let's proceed by taking kinetic energy. Kinetic energy, the formula is half mv square. Half being a number has no dimension, is a dimensionless quantity. Okay, now mass has a dimension capital M. Square of velocity. Velocity is L upon T, and the square of velocity will be L square upon T square, right? L square upon T square. So the dimension would be ml square T raised to the power minus 2. This is the dimensional formula of energy, and we will say 1 in mass, 2 in length, and minus 2 in time are the dimensions of energy. If we had taken potential energy, gravitational potential energy, instead of taking kinetic energy, let's see the dimension. The final answer should be the same because both are energy, right? So gravitational potential energy, the formula is mgh. M has mass, has a dimension m. G is acceleration due to gravity, that means it is acceleration, right? So acceleration is meter per second square, L upon T square, right? And h is height, so it is a length, and length has dimension L. Let's see what answer we get. M L square T raised to the power minus 2. Same answer, right? Let's talk about moment of inertia. Okay, just remember the formula. I know that you are not familiar with many terms. Just remember the formula. In your subsequent chapters you will come across these terms and you will learn about them in detail. Momentum, sorry, not momentum. Moment of inertia, the formula is mass into distance ka square. Okay, mass into square of distance. This is the formula of moment of inertia. So we will get mass has dimension m and distance square, that means square of a length L square. So the dimension came out to be ml square T raised to the power 0, because we normally express dimensional formula in terms of ml and T. Okay, what we would say, the dimension of moment of inertia is 1 in mass, 2 in length, and 0 in time, and this expression is the dimensional formula of moment of inertia. Clear? Number 11th, we have taken work, we have taken power, moment of inertia. Let's talk about torque. Torque is force into distance into angle between force and sine of the angle between force and distance. Okay, dimension of force is ml T raised to the power minus 2. This is distance, so it's a kind of length, dimension L. Sine theta has no dimension because it's a number. Numbers has no dimension, so our dimension came out to be ml square T raised to the power minus 2. This is the dimensional formula of torque, and we would say 1 in mass, 2 in length, and minus 2 in time are the dimensions of torque. Let's take stress. Stress is force upon area. Force has dimension ml T raised to the power minus 2 upon area. Area is a square of a length, this. So the dimension of stress came out to be ml raised to the power minus 1 T raised to the power minus 2. Right? This is the dimensional formula of stress, and we would say 1 in mass, minus 1 in length, and minus 2 in time are the dimensions of stress. Let's find the dimensions of few other physical quantities. Strain. Strain, the formula is change in length upon original length. So suppose there is a wire and you are stretching it, then you are causing a change in its length, right? So the change in length that occurred divided by the original length the wire had is known as strain. So change in length, we can say delta L, change in length upon original length. Since change in length is also a length, 3 elephant minus 2 elephant is also elephant, 1 elephant, right? Change in length is also a length, so it would have the same dimension of length, that is L, and length is a length, so it would again have the dimension L. So our final dimension came out to be M0, L0, T0. So strain is a dimensionless quantity. It has no dimension, right? It has no dimension because it is not depending upon any base physical quantities, right? Not depending upon mass, neither length, neither time. Let's take impulse. Impulse is force into the time interval. Delta t is the time interval for which the force acts. Okay. Impulse is the product of force and the time interval for which the force is acting. The product of force and the time interval. So we would say force has dimension mlt raised to the power minus 2. We have already derived it. And delta t is a time change. Delta t is a time interval. Final time minus initial time is a time interval, right? So it is time, and time has dimension t. mlt raised to the power minus 1. So the dimensional formula of impulse came out to be mlt raised to the power minus 1, and we would say that dimensions of impulse is 1 is mass, 1 in length, and minus 1 in time. See, impulse is force multiplied by the duration of time for which the force is acting. Okay. You will learn about it, don't worry. Just remember the formula, because that is the only thing that is needed to find the dimension of physical quantities. Let's take some more physical quantities. Let's find the dimensions of charge. Okay, we know that Q is equals to IT, right? I is equals to Q by T. Rate of flow of charge is called current. We know it. Okay. So from this formula, we get I, current, has a dimension A, and time has a dimension T. So AT is the dimension of charge. See, it is not always necessary that we will get the dimensional formula in terms of M, L, and T, right? Because any physical quantity may depend upon one or more of the remaining 4 fundamental physical quantities also. Here, charge doesn't depend upon length and mass. It only depends upon time and current. Okay? So we are getting the dimensional formula as AT. This time it is not necessary to mention length and mass in this formula. Okay? It is understood whenever a fundamental quantity is not appearing in the dimensional formula of a derived quantity, it is self-understood that the power to which that fundamental quantity has been raised is 0, right? Since mass is not present here, that means mass has been raised to 0 power in this case. Length has been raised to 0 power in this case. Luminous intensity, amount of substance has been raised to 0 power in this case, right? It is self-understood. Surface tension. Surface tension is force upon length. Since force has dimension mlt raised to the power minus 2, dimensional formula, and length dimension L. So the dimension of surface tension came out to be m L raised to the power 0. This L and this L will cancel out, and T raised to the power minus 2. This is the dimensional formula of surface tension, and we will say that the dimension of surface tension is 1 in mass, 0 in length, and minus 2 in time. Clear? In circular motion, we will talk about angular velocity, angular acceleration, etc. Okay, because in that chapter we will be dealing with motion in a circle, right? Let's start with frequency. Frequency is 1 upon time. The formula of frequency is 1 upon time. So talking about dimension of frequency, it would be 1 upon what? T. That is T raised to the power minus 1. M raised to the power 0, L raised to the power 0, T raised to the power minus 1. Then angular velocity. we know about linear velocity, that is the rate of change of displacement is linear velocity. Okay. Similarly, angular velocity means the rate at which you are covering angles while moving along the circumference of a circle. The rate at which you are covering angles. Okay. So it would be angle covered, that means 30 degree. If in 2 seconds you are covering, say, let me give you an example. If in 2 seconds I reached here, starting from A, I reached B. Then in 2 seconds, I covered an angle of 90 degree. Okay. So my angular velocity will be, this is pi by 2 radian. This is the angle I covered. Angle covered upon time taken, 2 seconds. That is pi by 4 rad per second, radian per second. This would be my angular velocity. Angle covered in time t, then angle upon time is the angular velocity. And the SI unit of angular velocity is rad per second, radian per second, because this is, we are talking about plane angle. Okay. 90 degrees pi by 2 radian, we know. So angle covered, just like in case of linear velocity, we had displacement covered in time t. Okay. In this case, in case of angular velocity, we have angle covered in time t. Since angle has no dimension, okay, plane angle and solid angle has unit, both of them has units, but none of them has dimension. Okay. So the angle covered has no dimension. We can write it as 1 upon t. So t raised to the power minus 1. This is the dimensional formula of angular velocity, and we would say that the dimension of angular velocity is minus 1 in time. Let's talk about the dimension of Young's modulus. Young's modulus, you will learn about Young's modulus in properties of solids, and the formula is stress upon strain. That is, stress means force upon area, right? And strain means change in length upon original length. Since strain has no dimension, we have already seen it. Just focus on force upon area. Force has dimension mlt raised to the power minus 2 upon area. Area is length into breadth, right? Area is length, is length into breadth. That means one length being multiplied with another length. That means L square would be the dimension of area. So the dimensional formula of Young's modulus came out to be ml raised to the power minus 1 t raised to the power minus 2. Right? We ignored this del L upon L because it is a dimensionless quantity. Both in the numerator as well in the denominator we have length. So both of them will cancel out. This is the dimensional formula of Young's modulus, and we would say 1 in mass, minus 1 in length, and minus 2 in time are the dimensions of Young's modulus. You will come across this term in properties of solids. Electric potential. Electric potential. The formula for electric potential is work done upon charge. Work done upon charge. And we know that the dimension of work done is, let me derive again, okay? Because the entire thing is new for you, so let me derive again. Work done is force into displacement into cos of the angle between force and displacement upon charge. Charge is what? We have Q upon T, rate of flow of charge is current. So from here we can write Q is equals to I into T. So it would be F into force into displacement into cosine of the angle between force and displacement upon charge is IT. Force is mlt raised to the power minus 2. We have already derived the dimensional formula of force. Displacement is a length, so its dimension would be L. Cos theta has no dimension. Upon I, current is a fundamental quantity, has dimension A. Time, dimension T. So the dimensional formula of electric potential came out to be M L square L to the power 1, L to the power 1. T raised to the power minus 3, A raised to the power minus 1. This would be the dimensional formula of electric potential. And what we would say? We would say the dimensions of electric potential is 1 in mass, 2 in length, minus 3 in time, and minus 1 in current. Let's talk about the dimensional formula of capacitance. the dimensional formula of capacitance. You will come across capacitance in class 12th under electricity. Okay. For the time being, just remember the formula, that is Q is equals to CV, where V is potential, electric potential, right? C is capacitance, Q is charge. From here, we get C is equals to Q upon V. Now we have the formula for capacitance. Okay. Charge is IT, that means A into T. We have derived the dimensional formula of charge already. Upon voltage is W upon Q. We just derived, but I forgot, so let me derive again. Voltage is W upon Q, that is mL square T raised to the power minus 2 upon charge. Charge is AT. Okay, mL square T raised to the power minus 3 A raised to the power minus 1. This would be the dimensional formula of voltage. So we would write mL square T raised to the power minus 3 A raised to the power minus 1. Clear? Dimensional formula of capacitance would be what? M raised to the power minus 1, L raised to the power minus 1, T raised to the power minus 3, and 1 T raised to the power minus 2, and A square. This would be the dimensional formula of capacitance. So now I think we can talk about the meaning of dimension. Dimension is what? Dimension is the pass to which the fundamental physical quantities are raised to express any derived physical quantity, right? See, if two quantities has the same unit, they must have the same dimension also. There are quantities which have unit but no dimension, like the supplementary quantities. Plane angle has unit radian but has no dimension. Solid angle again has a unit steradian but again has no dimension. Okay, now let's talk about application of dimensions. We are going to study total 3 applications of dimensions, starting with the first one, that is homogeneity of dimensions in an equation. Okay, see, using dimensional analysis, okay, we can check whether a given equation is dimensionally correct or not. If the equation is dimensionally correct, it may or may not be correct in the real situation. But if an equation is dimensionally wrong, it must be wrong. Clear? Now, let's first see what is the basis of the homogeneity of dimensions in an equation. What is the basis of this application? The basis is that we can only add or subtract similar quantities. 3 elephant plus 5 elephant is 8 elephant. 1 marker plus 10 marker is 11 marker. 2 people plus 3 people is 5 people, right? But 3 elephant plus 10 apple is nothing. You cannot add or subtract 2 dissimilar quantities. So in any equation, if say a number of terms are being added or subtracted, then the dimension of each term must be the same, okay, for that given equation to be dimensionally correct. Term means every entity appearing in an equation that is being added or subtracted to some other entity is known as term. Like we have S is equals to ut plus half at square. This is the equation of motion for one dimension with constant acceleration. Okay, here S is distance, u speed, acceleration a, t time. Let's check whether this equation is dimensionally correct or not. Distance dimension would be L. The dimension of each term should be same for this equation to be dimensionally correct. So the dimension of S came out as L. The dimension of ut would be u, that is velocity, meter per second, L t raised to the power minus 1 multiplied by t, time, plus half. We are writing the dimensions of each of these quantities. Acceleration meter per second square, that means L t raised to the power minus 2 square of time, dimension would be t square. So t raised to the power minus 1 and t will cancel out, plus half, sorry, no need to write half. 1 by 2 being a number is dimensionless, so just ignore it. We are only writing dimensions here. And t raised to the power minus 2 and t square will cancel out. So the dimension of each term S, ut and half at square came out to be L. So this equation is dimensionally correct. Actually, we know that this equation is correct in the real situation also. Now, there is an obvious limitation of dimensional, principle of homogeneity of equation. Okay, that limitation is that you can put any constant anywhere in this equation. Okay, you can put any constant anywhere in this equation and still this equation would be dimensionally correct, because numbers, pure numbers, has no dimension. They are dimensionless. So even 2s is equals to ut plus half at square is dimensionally correct, but it is not a correct equation, right? Even 2s is equals to 3 ut plus half at square is dimensionally correct, because still the dimension of s, this term 2s, 3 ut and half at square all are same and all are L, right? So it is not always necessary that an equation which is dimensionally correct should be correct. It may or may not be correct, right? An equation which is dimensionally correct may or may not be correct, but in an equation which is dimensionally wrong is always wrong. Because in any equation, if you are adding or subtracting two quantities which are dissimilar in nature, then it must be wrong. It is obvious. Okay, let's check. Let's check the dimensional correctness of few other equations. Like we will take simple equations only, because my aim is to make you understand the concept. V square is equals to u square plus 2s. Again, an equation of motion for one dimension, right? With constant acceleration. V, velocity, meter per second, L t raised to the power minus 1 would be the dimension. For this equation to be dimensionally correct, there are three terms, because three terms are being added or subtracted with each other. Okay, V square, u square and 2as. There are three terms in this equation and each term should have the same dimension, whatever dimension it is, but each of them should have the same dimension. Let's see. L t raised to the power minus 1 is the dimension of V square. Dimensional formula of V square. Most of the times people say that the term enclosed in the square bracket is dimension. No, it is not true. We generally do that, but always keep it in mind that this is a dimensional formula. Okay. Even I am saying that the dimension of V square is L t raised to the power minus 1. No, it's not true. The dimension of V square is 1 in length and minus 1 in time. This is the dimensional formula of V square. So always keep it in your mind. U square, that is again its square of a velocity. So L t raised to the power minus 1. V square, so it would be L square t raised to the power minus 2, right? And U square, so it would be L square t raised to the power minus 2 plus 2, being a pure number, is dimensionless. Acceleration meter per second square, that is L t raised to the power minus 2 into a distance, that is L. So this is also L square t raised to the power minus 2, right? So the dimensional formula, or I will just say simply, I will just say dimension. Okay, the dimension of each term is same, right? So this equation is dimensionally correct. Now again, let's talk about the limitation. Even half V square is equals to u square plus 2as is dimensionally correct. Still each of these terms have the same dimensions, right? Because a pure number has no dimension. You can put any number anywhere in this equation and still this equation would be dimensionally correct. So again, I'm saying an equation which is dimensionally correct need not be correct in the actual situation, but an equation which is dimensionally wrong is always wrong, right? Let's take an example. Let's take problem. Suppose the distance traveled by a particle in time t, is given by a plus bt square plus ct cube, a plus bt say plus ct square plus dt cube. Okay, the distance traveled by a particle in time t is given by this. You have to find out the dimension of a, b, c and d. See, since these terms are being added to each other or subtracted to each other, okay, there are 1, 2, 3, 4 and 5 terms in this equation. So since it is given in the question that this is the equation, this is the distance traveled by the particle in time t, So this equation must be correct. That is why it is given in the question. So since this equation is correct, this equation must be dimensionally correct also. So the dimension of each of these terms should be the same. S is the distance, it is given. The distance traveled by a particle in time t is given by this equation. So S is the distance. So distance is a length. So the dimension of S is L. So hence the dimension of each of these terms should be L. Okay. So the dimension of A should be L. This is our first answer. We were asked to find the dimension of A, B, C, and D. Now, the dimension of B, that we know that it is multiplied with time. Okay, so time has dimension T, and the dimension of B would be LT raised to the power minus 1, right? Because only this multiplied with this would give the dimension as L, T to the power minus 1, and T would cancel out each other. So the dimension of B is LT raised to the power minus 1. Similarly, the dimension of C would be LT raised to the power minus 2 into T square, because this in this term T square, the dimension of T square is this T square. Hence the dimension of C must be LT raised to the power minus 2 to make the product L. Okay. So this is the dimension of C. Similarly, you can find the dimension of D also. Okay. It would be LT raised to the power minus 3. The dimension of D would be LT raised to the power minus 3. So that's it. Let's move to the second application of dimension. Let's see the second application of dimension, that is to convert the unit of a derived physical quantity from one system of unit to other. Say from SI to CGS, or from CGS to SI, from CGS to MKS, from MKS to SI, right? When it comes to converting the unit of a fundamental quantity, it is very easy, because normally we know the factor of multiplication, right? The conversion factor. For example, if I wish to convert 1 kilogram to gram, I know that I have to multiply it with 10 raised to the power 3. So the conversion factor in this case is 10 raised to the power 3, because this is the number I have to multiply with 1 kilogram to get the value in grams. Clear? And gram is the unit of mass in CGS. So here we are converting from SI to, we are changing from SI to CGS system of unit. Okay, we are shifting from SI to CGS system of unit. Now, in case of derived quantity, that this task is not as easy. Okay, and to make it easier, we have the tool of dimension. Let's see how. We know that Pascal is the unit, SI unit of pressure, right? Pascal is the SI unit of pressure. And now, someone asked me to convert 1 Pascal into CGS system. I don't know the value, because I don't know the conversion factor here. In that case, I knew the conversion factor, that was 10 raised to the power 3. But in this case, I do not remember the conversion factor. I don't know the conversion factor. So I can get the conversion factor using dimensional analysis. Let's see how. First, let's find the dimension of pressure. Pressure is force upon area, that is mLT raised to the power minus 2 upon area L square, that is mL raised to the power minus 1 T raised to the power minus 2. Clear? So this is the dimension of pressure. We can write that in SI system, 1 Pascal of pressure is equals to mass, as in SI system, the unit of mass is 1 kilogram into the unit of length is what? SI system meter, 1 meter raised to the power minus 1 time 1 second raised to the power minus 2. This is in SI system. Now, let's say that in the CGS system of unit, the value of 1 Pascal is 1 CGS unit. 1 CGS unit, I don't know the value of this unit. We will derive it using dimensional analysis. So in CGS, we have gram for 1 gram into 1 centimeter, centimeter for length, gram for mass, whole to the power minus 1, and 1 second whole to the power minus 2. Clear? Let's say this equation is 1, this equation is 2. I'm just putting the values of mass, length, and time in SI and CGS. I'm not doing anything else. Now, dividing equation 1 and 2, we get 1 Pascal upon 1 CGS pressure, the value of which we still don't know, is equals to 1 kilogram upon 1 gram into 1 meter upon 1 centimeter whole raised to the power minus 1 into 1 second upon 1 second whole raised to the power minus 2. We will get this would be equals to 1000 grams. So 10 raised to the power 3 into 1 meter 100 centimeter 10 raised to the power 2. Sorry, here the power is minus 1, so it would be 10 raised to the power minus 2, and this entire thing will cancel out. So from here we get the conversion factor as 10. So we can say that to convert, see, 1 Pascal is equals to 10 CGS unit. Okay, 1 Pascal is equals to 10 CGS unit. So now we have our conversion factor. 1 Pascal is 10 CGS unit, hence to convert 1 Pascal into CGS system of unit, we will get 10 unit. The conversion factor is 10. And now what this unit is, okay, since I know it, I can tell you. In CGS system, the unit of pressure is dyne per centimeter square. Dyne per centimeter square. Okay, in CGS system, the unit of pressure is dyne per centimeter square. But what we were required to find was just the conversion factor. 1 Pascal is equals to 10 CGS unit. That's what we needed to answer. Okay, 1 Pascal is 10 CGS unit. I can tell you that for your information, that in CGS system of unit, the unit of pressure is dyne per centimeter square. See, Pascal is nothing but, what is Pascal? Pascal is just another name for Newton per meter square. So in CGS, this is SI system. In CGS system, the unit of force is dyne and the unit of length is centimeter. So in CGS system, the unit of pressure is dyne per centimeter square. So we can say that 1 Pascal is equals to 10 dyne per centimeter square. Okay. The third application of dimension is that the tool of dimensional analysis helps us to deduce relationship among physical quantities. So if we know that a given physical quantity depends upon a few other physical quantities, and this relationship is of product type, that means there are not more than 2 terms in that relationship, in that equation, forming that relationship. Okay, then we can deduce that relationship using dimensional analysis. Let's see how. We know that this is a simple pendulum, this is the string, this is a bob of mass m. The formula of time period is 2 pi upon 2 pi root under L by G. This is the formula of time period of this bob, okay, in simple harmonic motion. So we can reach very close to this equation using the tool of dimensional analysis. Let's see how. This is a product type equation. T is depending on only one term, nothing is being added to this term. Okay, so this is a product type equation. In a product type equation, there is only 2 terms. Here T is the first term, this is the second term. Okay, now suppose I know it from somewhere that T depends upon mass raised to the power A. That means some power of mass. T depends upon mass. Okay, some power of mass of which we have no idea. For the time being, we have no idea. Length raised to the power B and gravitational constant raised to the power C. I know it from somewhere. Okay, now let's convert the sign of proportionality to equality. T would be equals to K m raised to the power A, L raised to the power B, G raised to the power C, where K is a dimensionless constant. Okay, now let's deduce. You will see that we will come very close to the true equation using dimensional analysis. Let's see how. Take dimensions both sides. This is time period, so it is time. Dimension would be T. K has no dimension, it's a true number, it's a pure number. Mass m, m raised to the power A, L raised to the power B. G is acceleration due to gravity, that means L t raised to the power minus 2. meter per second square whole to the power c. So L raised to the power c, t raised to the power minus 2c. Clear? So from here we get m raised to the power a, L raised to the power b plus c, t raised to the power minus 2c. Now let's compare both sides. Here we can write it as m raised to the power 0, L raised to the power 0, t. Okay. So from here we get a equals to 0. A equals to 0. B plus C is equals to 0 and minus 2C is equals to 1. From here we get C is equals to minus 1 upon 2. Putting C equals to minus 1 upon 2 in equation 2, we will get B minus 1 by 2 equals to 0. This implies B equals to 1 by 2. So now we know all the powers. Just put it in this equation. Put it in this equation. T is equals to this. We would get KT is equals to K m raised to the power A, m raised to the power 0, L raised to the power B, L raised to the power 1 by 2, and G raised to the power C, that is G raised to the power minus 1 by 2. We can write it as K root under L upon G. There is an obvious limitation of this application, that this constant is still unknown, because there can be any constant here. Constant has no dimensions. Okay, so you have to know the value of K from somewhere else, by experiments, by conducting experiments or something else. You have to know the value of K from somewhere else and then put it here to make this equation complete. This is the limitation of this application. Dimensional analysis never tells us anything about the constant. Okay, this was the same limitation we talked about while discussing the first application of dimensional analysis. Okay, so T is equals to K root under L upon G. Again, dimensional analysis helps us to reach very close to the exact equation. Okay, to reach very close to the exact equation only if the relationship is of product type. Here the relationship is of product type. If it were not of product type, we couldn't have deduced it using dimensional analysis. For example, say V is equals to U plus AT. You cannot deduce this relationship using dimensional analysis, because this is not a product type relationship, right? There are more than 2 terms in this equation. 1, 2, 3 terms. Similarly, S is equals to UT plus half AT square. We can never deduce or come close to this equation using dimensional analysis, because this is again not a product type equation. Another limitation of the third application is that you can deduce the relationship among physical quantities only if there are as many equations available as the number of variables. Here, the number of equations we had was 3. M raised to the power A, it was M0, L0, T1. So we had 3 equations and 3 unknowns. 3 unknowns A, B, and C, and 3 equations. The first was 0 is equals to A. The second was 0 is equals to B plus C, or B plus C equals to 0, whatever. And the third one was minus 2C is equals to 1. So you can apply the concept of dimensional analysis to deduce a relationship only if you have as many variables as the number of equations available, right? This is the third limitation of dimensional analysis.